The universe spent its first 100 million years in absolute darkness. No stars, no light, only a vast sea of neutral hydrogen gas and the invisible grip of dark matter stretching across an empty void. Then something changed. Deep inside collapsing clouds of primordial gas, the very first stars ignited. They ended the cosmic dark ages and began building the first structures out of nothing. Why does this matter for understanding our own origins? Because those ancient stars set the stage for every galaxy, every planet, and every living thing that followed. By the end, you will see how a few ancient stars turned a blank cosmos into the blueprint for everything we know. How did stars form when there were no ingredients except hydrogen and helium? What force took a cold, dark void and lit it up? This journey follows the timeline from the Big Bang aftermath to the emergence of galaxies, with the first stars as the pivotal agents of change. We will explore how they formed, lived furious short lives, and died in explosions that scattered the first heavy elements across space. What does it mean that we are made of the remains of these long-gone giants? Before those giants appeared, the universe endured a long, silent night. For hundreds of millions of years after the Big Bang, there was not a single point of light anywhere. No stars, no galaxies, no beacons of any kind. This period is known as the Cosmic Dark Ages, and it began roughly 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to finally combine into neutral hydrogen and helium atoms. That event, called recombination, released a flash of light we now detect as the cosmic microwave background. But once that light faded away, the universe became transparent and almost featureless. It was filled with an even, cold fog of neutral gas. No structures had formed yet, no heat sources, no radiation except the faint, fading glow of the Big Bang itself. For the next 100 million years or more, the cosmos was a place of profound emptiness and quiet. Gravity was already at work, slowly pulling clumps of dark matter together into invisible halos. But ordinary matter, the hydrogen and helium, could not follow right away. It was too hot, too spread out, too evenly distributed. The universe needed time, and it needed a scaffold. That scaffold came from dark matter. As dark matter gathered under its own gravity, it created deep gravitational wells, like invisible basins in the fabric of space. Into those basins, the neutral gas began to slowly trickle, gathering in denser and denser pockets. It was a slow process, almost imperceptible on human timescales. But across millions of years, those pockets grew, cooled, and eventually reached a critical threshold. The cosmos was stockpiling fuel for a transformation that would end the Dark Ages forever. What happened next, when the first spark finally appeared, would remake the universe. Dark matter provided the skeleton that ordinary matter could cling to. Unlike the hydrogen and helium gas that filled the early universe, dark matter did not interact with light or any electromagnetic force. It could not be pushed apart by radiation pressure or heated by nearby energy sources. It only felt gravity. So while the neutral gas remained spread out and reluctant to gather, dark matter clumped together relatively quickly, pulled by its own mutual attraction. These clumps grew slowly at first, then faster as more material fell in, forming vast, roughly spherical clouds known as dark matter halos. Each halo was an invisible gravitational basin, a region where the pull of dark matter was strong enough to trap anything nearby. And there was plenty of material nearby, the neutral hydrogen and helium that still filled most of space. As gas drifted into these dark matter wells, it began to accumulate. The halos acted like cosmic reservoirs, collecting the primordial gas into denser and denser pockets. Without the dark matter halos, that gas would have remained too diffuse to ever collapse under its own weight. Gravity alone on the hydrogen, weak and spread thin, would not have been enough. But with the extra gravitational pull from the dark matter, the gas could concentrate. It was like having a hidden hand pushing everything together, making collapse possible for the first time in the universe's history. This process did not happen all at once. The early universe built its structures hierarchically. Small halos formed first, each perhaps a few 100,000 times the mass of the Sun. Those small halos then merged over time, combining into larger ones, like snowflakes rolling into a snowball. Each merger stirred up the gas, sending shock waves through the cloud and creating denser knots where gravity could work even more efficiently. This hierarchical growth was the engine that drove structure formation from the smallest scales upward. It meant that the very first stars likely appeared inside the smallest halos in the quietest corners of the cosmos, long before any galaxies existed. The dark matter halos were the unbreakable seed capsules that protected and concentrated the raw material of stars. They provided the gravitational scaffolding on which everything else would be built. Without them, the universe might have remained an endless cold fog with no points of light ever flickering to life. Instead, inside these invisible bowls, the gas grew steadily denser, cooler, and more compact, approaching the critical threshold for collapse. The stage was set for the final act of the Dark Ages, the moment when a cloud of gas, squeezed by the silent hand of dark matter, would ignite and become the very first star. As gravity pulled gas into those dark matter halos, something strange happened. The gas did not simply pile up quietly. As it fell deeper into the gravitational well, it compressed. And compression, as any physics student knows, heats things up. The primordial hydrogen-helium atoms began to move faster, colliding more often, raising the temperature of the cloud. This heating was a problem. For a gas cloud to collapse further and eventually ignite a star, it must shed that heat. It must radiate energy away into space. Otherwise, the pressure from the heat would resist further compression. Like a balloon you try to squeeze that fights back. The cloud would stall, unable to condense into a dense enough core. But here lay the crisis. Hydrogen and helium are terrible at cooling at low temperatures. They are simple atoms. When they collide, they rarely emit any energy. They just bounce off one another, heaping the heat trapped inside the cloud. For hundreds of millions of years, this cooling crisis prevented the universe from forming any stars at all. The gas could not find a way to let go of its heat. Yet nature found a workaround, a clever and fragile one. It involved a molecule called molecular hydrogen, or H2. Unlike single hydrogen atoms, two hydrogen atoms bonded together have a slightly more complex structure. That tiny complexity allows them to vibrate and rotate, and when they do, they can emit small amounts of energy as infrared light. This emission is weak, but it is enough. The catch is that molecular hydrogen is very rare in the early universe. There were no stars yet to produce it, no complex chemistry. It had to form from scratch in the thin gas using a handful of leftover electrons from the recombination era. Those electrons acted as catalysts, helping two hydrogen atoms stick together long enough to form a molecule. It was a slow, inefficient process. Only a tiny fraction of the hydrogen turned into molecular hydrogen, perhaps one molecule for every 100,000 atoms. But that tiny fraction was enough to become the primary coolant for the first collapsing clouds. As the gas in a dark matter halo compressed and heated, those rare H2 molecules absorbed some of that energy and then re-emitted it as infrared photons. Those photons flew away into space, carrying the heat with them. Bit by bit, the cloud cooled. The cooling was agonizingly slow compared to modern star formation, where dust grains and many other molecules help shed heat quickly. Here, the cooling depended on a trace amount of molecular hydrogen. That inefficiency had a profound consequence. Because the gas cooled slowly, it could not easily fragment into many small clumps. Instead, the entire cloud kept contracting as a single massive blob. It kept pulling in more and more material, growing ever denser and hotter, until finally the core reached temperatures and pressures high enough to ignite nuclear fusion. The result was not a small star like our Sun. The result was a giant, perhaps dozens of times more massive than the Sun, sometimes even hundreds of times. These were the first stars, the universe's earliest giants. They burned fiercely, lived fast, and died young. But before they could even form, a delicate balance had to hold. The cloud had to cool just enough to collapse, but not so fast that it broke apart into tiny pieces. It had to rely on a rare molecule that barely existed, and the dark matter halo had to provide just the right gravitational anchor. It was a narrow path, a thin thread of possibility that the universe threaded perfectly. And once that first collapse succeeded, the cosmic dark ages ended in a flash of light that has never truly faded. That first collapse took millions of years to reach its breaking point. Deep inside a dark matter halo, a cloud of primordial hydrogen and helium had been slowly contracting, cooled by the faint glow of rare molecular hydrogen molecules. The cloud was enormous, containing perhaps 100,000 times the mass of our Sun, all spread out over a region many light years across. But gravity kept pulling it inward, and the cooling kept just barely ahead of the heating, allowing the collapse to continue. As the cloud shrank, its center grew denser and hotter. Pressure built. The atoms and molecules jostled faster and faster. At some point, the core reached a temperature of about 10 million Kelvin, the threshold where hydrogen nuclei can slam together with enough force to overcome their mutual repulsion and fuse into helium. That fusion released an immense burst of energy, enough to halt the collapse and create a stable star. But this star was nothing like the ones we see in the sky today. Modern stars form in giant molecular clouds that contain not just hydrogen and helium, but also heavier elements like carbon, oxygen, and iron, along with tiny grains of dust. Those metals and dust make cooling incredibly efficient. As a modern cloud collapses, it breaks apart into many small fragments, each fragment forming a separate star. That is why most stars in our galaxy are relatively small, like our Sun, or even smaller. The first stars had no such advantage. Their clouds contained only hydrogen and helium, with just a trace of molecular hydrogen for cooling. That cooling was so weak that the cloud could not fragment into tiny pieces. Instead, the entire massive clump kept contracting as a single object, pulling in everything around it. The result was a star that was not small, but monstrous. A star with a mass tens to hundreds of times greater than the Sun. Astronomers call these first stars population 3, a designation that goes back to a classification system for stars based on their metal content. Population 3 stars are pure primordial beasts, with almost no heavy elements at all. They were the universe's first nuclear furnaces, and they burned with a ferocity that is hard to imagine. Their surface temperatures could exceed 40,000 Kelvin, making them appear blue-white and incredibly bright. A single one of these giants could outshine an entire galaxy of modern stars, but that brilliance came at a cost. The more massive a star is, the faster it consumes its nuclear fuel. While our Sun will burn for 10 billion years, a population 3 star of 100 solar masses would exhaust its hydrogen supply in just a few million years, a cosmic blink of an eye. And when such a star runs out of fuel, its fate is not a quiet fade. It ends in a catastrophic explosion that scatters newly forged heavy elements across the cosmos. Those elements would become the seeds for the next generation of stars, and eventually for planets and life. But before that, we must understand what it was like inside these fiery giants and how their extreme properties shaped the universe around them. These stars were not simply large, they were fundamentally different from anything that exists today. Their surfaces blazed at temperatures exceeding 100,000 Kelvin, more than 15 times hotter than the surface of our sun. At such extreme heat, the light they emitted was not mostly visible. It was overwhelmingly ultraviolet, a torrent of high-energy radiation that could tear apart atoms. Luminosity-wise, a single first star could outshine 1,000,000 suns combined. But that brilliance came with a terrible price. The star burned through its nuclear fuel at a staggering rate. While our sun converts hydrogen into helium at a steady, calm pace over billions of years, a population 3 giant devoured its fuel in just a few million years. That is an astronomically short lifespan, barely a cosmic heartbeat. Why did they burn so fast? Because they were so massive. Their immense gravity squeezed their cores to extreme pressures and temperatures, forcing hydrogen nuclei to fuse at an incredible rate. The result was a furious, wasteful burn that released enormous energy but could not sustain itself for long. Their interiors churned with violent convection, mixing fresh hydrogen into the core and keeping the flame roaring until the very end. Because these stars contain almost no metals, they lacked the usual mechanisms that modern stars use to shed mass. Our sun, for example, has a steady solar wind driven by its magnetic field and by radiation pressure on dust and ions. That wind slowly carries away mass over time. But the first stars had no dust. Their atmospheres were pure hydrogen and helium, with just a trace of other light elements. Without dust, the radiation pressure could not push material away effectively, so they held on to nearly all their mass throughout their lives, growing even more massive as they continued to accrete gas from their surroundings. As a result, they remained colossal until the very end. The intense ultraviolet radiation they produced did not just light up the universe, it transformed it. Each photon carried enough energy to knock electrons off hydrogen atoms, a process called ionization. For hundreds of millions of years, the universe had been filled with neutral hydrogen gas, opaque to most forms of light. But these first stars began to punch holes in that fog, creating expanding bubbles of ionized gas around themselves. Those bubbles grew and merged over time, gradually turning the cosmic landscape from a neutral haze into a transparent, ionized medium. This process, known as reionization, was one of the most important transformations in cosmic history. It allowed light to travel freely across the universe for the first time, paving the way for us to see distant galaxies billions of years later. But the stars themselves could not last. Their nuclear furnaces burned ferociously, and when the fuel ran low, they faced an inevitable collapse. That collapse, when it came, was not a quiet end. It was a catastrophic explosion that would seed the cosmos with the first heavy elements, laying the foundation for everything that followed. The stage was set for a dramatic exit. When their nuclear fuel finally ran low, the most massive of these first stars faced a fate unlike anything that had come before. For a star with more than 100 times the mass of our sun, the end was not a quiet collapse into a black hole. It was a complete and total disruption, an explosion so powerful that nothing survived. This event is called a pair instability supernova, and it arises from a strange quirk of physics inside the star's core. As the core's temperature climbed to extreme levels, exceeding 1 billion degrees, photons of light became so energetic that they could spontaneously transform into pairs of particles, an electron and its antimatter counterpart, a positron. This process, called pair production, suddenly drained energy from the core. Without that energy to provide pressure, the core could no longer support the immense weight of the star above it. Gravity won. The core began to collapse. But this collapse did not lead to a neutron star or a black hole. Instead, it triggered a runaway thermonuclear reaction. The star's entire body, from its core to its outer layers, was consumed in a single, furious detonation. There was no remnant left behind, no compressed ball of neutrons, no dark, silent singularity. The star simply vanished, replaced by an expanding cloud of plasma and newly forged elements. That explosion released as much energy in a few seconds as the star had produced in its entire lifetime. The light from a single pair instability supernova could briefly outshine an entire galaxy of modern stars. And in that flash, the star scattered its enriched material across the cosmos. These explosions were not subtle. They blasted out heavy elements, carbon, oxygen, silicon, iron, and even heavier metals at speeds of thousands of kilometers per second. The pristine, metal-free universe suddenly received its first dose of chemical diversity. Those elements shot outward, mixing with the surrounding hydrogen and helium gas, seeding future generations of stars with the raw materials for planets and for life. But not every first star ended in such a dramatic obliteration. For those with masses below about 100 suns, the death was different. These stars, still enormous by modern standards, underwent a core collapse supernova. When their cores ran out of fuel, they collapsed inward, forming either a neutron star or a black hole, depending on their exact mass. The collapse itself released a tremendous burst of neutrinos and triggered a shock wave that blew off the star's outer layers. These explosions were also incredibly powerful, though not quite as cataclysmic as the pair instability variety. They too scattered metals into the surrounding space, enriching the cosmic environment with the elements that would later build rocky worlds. The energy of these supernovae was so great that they could influence the formation of nearby stars. Shock waves from one explosion could compress nearby gas clouds, triggering a new wave of star formation. That new generation of stars, born from gas now laced with metals, would be smaller, longer-lived, and more like the stars we see today. The first supernovae were the factories that produced the building blocks of complex chemistry. They turned a universe of only hydrogen and helium into a place capable of making planets and eventually, us. These explosions marked a turning point. The pristine, neutral gas of the cosmic dark ages became contaminated with metals, changing how future stars would form and evolve. The universe would never be the same. The first seeds of structure had been planted, and they were about to grow into something far more intricate. Those first explosions hurled the building blocks of complexity across space. The supernovae of the population 3 stars were like cosmic seed bombs, scattering newly forged elements in every direction. For the first time, the pristine hydrogen and helium gas that filled the universe became contaminated with metals. Astronomers call any element heavier than helium a metal, even though that includes familiar ones like carbon and oxygen. Before these explosions, the cosmos had none. Afterward, the gas glowed with the possibilities of carbon, oxygen, silicon, and iron. Each element had been pieced together inside the crushing cores of those ancient giants during their final moments of fusion. Then, in a flash, they were released into the surrounding medium. That contamination was irreversible and transformative. The presence of metals changed the behavior of the gas in a fundamental way. You see, pure hydrogen and helium are terrible at cooling. They can only radiate away heat through those rare molecular hydrogen molecules, as we saw earlier. But metals are far more efficient. A single carbon or oxygen atom can absorb energy from colliding gas particles and then emit that energy as infrared light much more readily than hydrogen ever could. Once even a tiny amount of metals entered the gas, the cooling rate skyrocketed. Clouds collapsing inside dark matter halos could now shed their heat much faster. That meant they could fragment into many smaller clumps rather than collapsing as one giant blob. Instead of forming 1 or 2 monster stars, a cloud could now produce dozens, hundreds, or even thousands of smaller stars. This shift gave birth to a new generation of stars, which astronomers call population 2. These stars still had very low metal content compared to our Sun, but they were no longer pure. They contained the chemical fingerprints of the earlier supernovae. Population 2 stars were smaller and lived much longer than their predecessors. Some of them survive today, and we can study them to read the history of early enrichment. Astronomers measure a star's metallicity by looking at the strength of absorption lines from elements like iron in its spectrum. Old stars with extremely low iron content are rare and precious. They are time capsules from the era just after the first supernovae. By comparing their composition to the yields predicted by supernova models, researchers can even identify which kind of explosion seeded the material. For example, some ancient stars show an unusual abundance of carbon relative to iron, hinting that they formed from gas enriched by a pair instability supernova from a very massive first star. So, each supernova was not just a flash of light. It was a chemical recipe, a unique blend of elements that mixed into the local gas. As that gas collapsed into new stars, it carried the signature of its parent explosion. Over time, successive generations of stars added more layers of complexity. Each supernova contributed a different set of elements, steadily increasing the overall metallicity of the universe. The gas became richer, the stars became smaller, and the cosmos began to resemble the one we see today. The transition from a metal-free universe to a chemically diverse one was the key that unlocked the formation of planets. Without metals, there could be no dust, no rocky worlds, no solid surfaces. The first stars turned the universe from a barren void into a fertile garden, scattering the seeds that would eventually grow into everything we know. And the process did not stop. It continued for billions of years, each generation adding its own contribution, making the cosmic recipe more intricate with every cycle. The story of the first stars is really the story of how the universe learned to build complexity out of simplicity, one explosion at a time. The gas that once held only hydrogen and helium now carried the fingerprints of ancient explosions. Tiny traces of carbon, oxygen, silicon, and iron drifted through the vast clouds inside dark matter halos. They were incredibly dilute. Maybe just one metal atom for every 10,000 hydrogen atoms, but that was enough to transform the universe forever. With metals present, the cooling landscape changed dramatically. A single carbon or oxygen atom could absorb energy from a colliding hydrogen atom and then radiate it away as infrared light far more efficiently than the rare molecular hydrogen molecules had ever managed. Clouds that previously struggled to shed heat could now cool in a fraction of the time. And fast cooling meant something crucial: fragmentation. Instead of one enormous blob of gas collapsing into a single monster star, the cloud could break apart into dozens, hundreds, or even thousands of smaller clumps. Each clump could then collapse on its own to form a star, but a much smaller one. These new stars were not the 100 solar mass giants of the first generation. They were typically between a tenth and a few times the mass of our Sun. They burned steadily, lived for billions of years, and some of them are still shining today. Astronomers call these stars population 2 because they formed from gas that had been enriched by the first supernovae. They mark the end of the era of the first stars. Not a sudden cutoff, but a gradual transition. For a time, both populations coexisted. Some regions of the universe remained nearly pristine, still producing the occasional massive giant. But as more and more supernovae exploded, the average metallicity of the cosmos crept upward. The days of pure primordial stars were numbered. The first galaxies began to take shape during this transition. They were not the grand spirals we see today. They were small, irregular collections of population 2 stars packed closely together inside dark matter halos. Each galaxy might have contained only a few million stars, but they were already producing complex chemistry. The era of simple giants had given way to an era of diverse stellar families, and the universe was becoming a place where planets could eventually form. The first star era did not end with a single event. It faded away as the gas became richer, one supernova at a time. The flood of ultraviolet light from those first giants did more than just illuminate the darkness. It actively reshapes the entire universe around them. Each star emitted an intense torrent of high-energy photons, each carrying enough energy to knock an electron clean off a hydrogen atom. This process is called ionization. For the first few 100 million years, the cosmos had been filled with neutral hydrogen gas, where each atom held its electron tightly. That neutral gas was opaque to most ultraviolet light, like a thick fog. But the first stars began to burn through that fog. Around each star, a sphere of ionized gas expanded outward. Inside that sphere, the hydrogen atoms had been split into free electrons and protons, a plasma state that was transparent. These bubbles were initially small, isolated patches of clarity in a vast, murky sea. But as more stars ignited across the universe, more bubbles formed. They grew and they began to touch. Imagine a frozen pond in early spring. The ice is solid and uniform, covering the entire surface. Then the first cracks appear. Pockets of open water form where the sun's warmth concentrates. Those pockets grow, merge, and eventually the ice breaks apart completely. That is reionization. The first stars were the sun that melted the cosmic ice. The ice was the neutral hydrogen fog, and the open water was the ionized plasma. This transformation did not happen overnight. It took hundreds of millions of years, perhaps a billion. The universe changed phase gradually, from neutral to ionized, one photon at a time. The stars themselves were the primary engines of this change, each one contributing its own torrent of ionizing light. The process was uneven. Some regions cleared early, while others remained neutral for longer. As the population of stars grew, so did the overlapping bubbles, until eventually the entire universe became transparent. This moment, the end of reionization, marks a major milestone in cosmic history. It allowed light to travel freely across vast distances, which is why we can now see galaxies from billions of years away. But the first stars were not the only players. Deep within the hearts of some of those collapsing giants, something else was born. The most massive stars, those that did not explode completely, left behind black holes. Those black holes began to grow, feeding on surrounding gas, and they too released fierce radiation that contributed to reionization. Their story would add a new chapter to the transformation of the early universe. Not every first star ended its life in a brilliant supernova. Some of these ancient giants simply collapsed inward at the end of their lives, forming black holes without any outward explosion. When a star with a mass between roughly 40 and 100 times that of our Sun exhausted its nuclear fuel, its core did not detonate. Instead, it imploded directly into a singularity, a point of infinite density. No light escaped, no heavy elements scattered. The star simply vanished from sight, replaced by a dark gravitational trap. These newly formed black holes were not huge by modern standards. They contained perhaps 10 to 100 times the mass of our Sun, but that was enough. They sat at the centers of their dark matter halos, surrounded by leftover gas that had not yet fallen into the star. That gas began to spiral inward, drawn by the black hole's immense gravity. As it fell, it heated up, reaching temperatures so extreme that it emitted powerful X-rays. Those X-rays were not just a side effect. They became a new source of energy in the early universe, competing with the ultraviolet light from stars. They could heat the surrounding gas, even in regions where starlight did not reach. Over time, those black holes grew, accreting more material. The growth was slow at first, but as the black holes merged with others and drew in ever larger quantities of gas, they swelled. Some of them became the seeds for the supermassive black holes we see at the centers of galaxies today, including the one that powers quasars in the early universe. There's even a more exotic possibility. Some of the very first primordial gas clouds might not have formed stars at all. Instead, they could have collapsed directly into a much larger black hole, skipping the star phase entirely. This process is called direct collapse. It would have produced black holes with thousands or even hundreds of thousands of times the mass of our Sun right from the start. Such objects would have been incredibly bright as they fed, perhaps outshining entire galaxies. Their X-rays would have heated the intergalactic gas on large scales, influencing how and where later stars could form. And because they were so massive to begin with, they could grow into the supermassive black holes observed just a few 100 million years after the Big Bang. Astronomers have detected quasars powered by black holes with billions of solar masses at cosmic dawn. How did they get so big so fast? Direct collapse offers one answer. The first black holes, whether born from star collapse or direct collapse, were not passive remnants. They were active agents of change, shaping the thermal and chemical evolution of the universe. Their X-rays helped reionize the gas, and their gravitational pull gathered the material that would build the first galaxies. The story of structure formation is not only about stars. It is also about the invisible giants they left behind. But the visible giants themselves also shaped their surroundings in powerful ways. The first stars were not passive lights in the darkness. They actively sculpted the gas around them through a trio of forces: radiation pressure, ionizing photons, and supernova blast waves. Each one left its mark on the cosmic landscape, influencing where and when the next generation of stars could appear. Radiation pressure came from the sheer intensity of the star's light. Photons carry momentum, and when billions upon billions of them stream outward from a blazing surface, they can physically push against nearby gas. In the case of the first stars, that push was immense. The ultraviolet light was so energetic that it literally shoved the surrounding hydrogen and helium away, clearing a bubble of low-density material around each star. This bubble could expand for hundreds of light years, depriving the region of the fuel needed for new stars to form. Then there were the ionizing photons. These high-energy particles stripped electrons from hydrogen atoms, converting neutral gas into a hot plasma. That plasma was much hotter than the neutral gas around it, so it exerted higher pressure and expanded outward. The expanding ionized bubble acted like a cosmic wind, sweeping up material and pushing it to the edges of the halo. In some places, this sweeping actually compressed gas at the bubble's boundary, triggering the collapse of new clouds and sparking additional star formation. So the same star that cleared its immediate neighborhood could also ignite new fires on its periphery. Finally, the supernova explosions delivered the most dramatic feedback of all. When a first star ended its life in a cataclysmic blast, the shock wave plowed through the surrounding gas at thousands of kilometers per second. That shock wave did two things at once. It drove the gas outward, often blowing it completely out of the dark matter halo, starving the region of material for millions of years. But it also compressed any clumps of gas it encountered along the way, sometimes triggering a burst of star formation in the compressed shell. The net effect was a delicate balance. Sometimes the feedback suppressed star formation by heating and dispersing the gas. Other times it triggered new waves of collapse, like a forest fire that clears old growth and makes way for new seedlings. This push and pull created a self-regulating cycle. Star formation produced feedback. Feedback limited further star formation until the gas had time to cool and settle again. Then the cycle repeated. The early universe did not experience a single burst of star formation that consumed all the gas at once. Instead, it proceeded in fits and starts, each generation of stars shaping the conditions for the next. This regulation was crucial. Without it, the first galaxies might have turned all their gas into stars in a runaway frenzy, leaving no fuel for later growth. Instead, feedback kept the process slow and steady, allowing galaxies to build up gradually over billions of years. The same forces that cleared gas away also mixed it with heavy elements, enriching the intergalactic medium. The result was a universe where star formation happened in waves, each wave leaving its imprint on the chemical and thermal state of the gas. As these feedback processes played out across countless dark matter halos, the first small galaxies began to assemble. They were not yet the majestic spirals we see today. They were chaotic, clumpy collections of stars, gas, and dark matter, shaped by the constant push and pull of stellar explosions and radiation. The stage was set for the next major step in cosmic evolution, the emergence of galaxies that could sustain multiple generations of stars, building complexity one cycle at a time. Out of that regulated chaos, the first true galaxies began to assemble. Imagine a cosmic stream of dark matter halos, each carrying its own small population of stars and gas drifting through the void. As the universe expanded and time marched forward, gravity pulled these halos together. They collided and merged, combining their contents like droplets of water merging into a larger pool. This process is called hierarchical assembly, and it is how every galaxy in the universe was built. The first proto-galaxies were tiny by modern standards, perhaps just a few million solar masses of stars and gas, huddled inside a dark matter halo 100 times more massive. When two such halos merged, their stars and gas did not simply pile up neatly. They sloshed, collided, and mixed. The gas, still mostly hydrogen and helium but now enriched with trace amounts of metals from earlier supernovae, was stirred into new configurations. Some of it fell toward the center of the newly combined system, funneled by gravitational interactions into a dense core. There, it ignited fresh waves of star formation. The star formation rates in these early galaxies were astonishingly high relative to their size. A small proto-galaxy might contain only a few million stars, but it could be forming new ones at a rate comparable to a modern galaxy, 100 times larger. The reason was the abundance of fuel. Gas was everywhere, and mergers kept delivering fresh supplies to the central regions. The stars being born were a mix of the last population, 3 giants, and the emerging population, 2 stars, smaller and longer lived. So these first galaxies were not uniform. They contained pockets of pure primordial gas that had somehow avoided pollution alongside regions already seasoned with carbon and oxygen. They were irregular in shape, often clumpy and asymmetric, lacking the elegant spiral arms or smooth elliptical forms we see today. Each merger also stirred the central black holes that had formed from the deaths of earlier massive stars. Those black holes, now nestled in the densest parts of the galaxy, began to feed on the gas being channeled inward. Their feeding generated fierce radiation and outflows, adding another layer of feedback to the mix. The black holes grew, and their activity sometimes quenched star formation by heating or expelling gas, only for later mergers to bring in more fuel and reignite it. It was a chaotic, dynamic process, far from the serene images of modern galaxies. But this was the crucible in which the first real galaxies formed. As more and more of these proto-galactic building blocks merged, they grew larger, richer, and more structured. Eventually, the universe reached a point where galaxies became the dominant structures, outshining the scattered individual stars that had once defined the cosmos. The Dark Ages had truly ended, not with a single event, but with the steady assembly of star cities, each one a complex ecosystem of light, gravity, and chemistry. The stage was set for the next cosmic acts, the rise of galaxies like our own Milky Way and the slow, patient evolution that would lead to planets, life, and us. 1 billion years after the Big Bang, the last islands of neutral fog dissolved forever. The ionized bubbles that had grown around each first star and early galaxy finally merged into a single connected web of transparent plasma. Imagine a vast patchwork quilt where each patch was a sphere of clear, ionized gas expanding outward at hundreds of kilometers per second. For hundreds of millions of years, these bubbles had remained separated by walls of opaque neutral hydrogen. But as more and more stars ignited and more galaxies assembled, the patches grew, their edges touched, and then they fused. The moment the last gap closed, the entire universe became transparent to ultraviolet light. This transformation is called the End of Reionization, and it marked a permanent shift in the cosmos. After that point, the intergalactic medium remained mostly ionized, meaning light could travel freely across vast distances without being absorbed. The cosmic fog had lifted for good. Roughly 1 billion years had passed since the Big Bang. The Dark Ages were over. The first stars and galaxies had accomplished something extraordinary. They had remade the fabric of the universe itself, turning a cold, opaque void into a transparent, glowing arena where future galaxies would shine. How do we know this happened? Astronomers have found direct evidence. When we look back in time at the most distant quasars, their light reveals the state of the intergalactic gas. We see absorption lines from neutral hydrogen that disappear at earlier times, marking the boundary of reionization. We also study the cosmic microwave background, which carries a subtle imprint of the ionized bubbles. By mapping these signals, researchers have pieced together the timeline of this great transformation. The light from the first stars, long since vanished, still echoes in the data we collect today. Those ancient giants, each burning for only a few million years, left a permanent mark on the universe that we can read billions of years later. Their legacy is written in the sky, waiting for us to decode it. Decoding that legacy requires instruments sensitive enough to capture whispers from 1 billion years ago. Astronomers have developed a toolkit of observational methods, each revealing a different piece of the story, and together they paint a coherent picture of the first stars and the reionization they drove. One of the most powerful tools comes from the cosmic microwave background itself. When the first stars ionized the surrounding hydrogen, they left a subtle imprint on the ancient light that has been traveling toward us since recombination. That imprint appears as a faint polarization signal in the microwave background, a kind of ghostly echo of the reionization process. By measuring how strongly the light is polarized, scientists can estimate when reionization began, how quickly it proceeded, and how much of the universe was ionized at different times. It is like reading a diary written in the very fabric of space. Another technique listens for a specific radio whisper from neutral hydrogen. Hydrogen atoms emit a faint radio signal at a wavelength of 21 centimeters. In the early universe, before reionization, vast clouds of neutral hydrogen filled the cosmos. Those clouds would have emitted that 21-centimeter line, but the signal has been stretched and redshifted over billions of years as the universe expanded. Today, that ancient emission arrives at radio telescopes as a weak, diffuse glow spread across a wide range of frequencies. Astronomers call this the 21-centimeter signal from the cosmic dawn. Detecting it is extraordinarily difficult because it is buried under much brighter radio noise from our own galaxy and from human technology. But a new generation of radio telescopes, such as the hydrogen epoch of reionization array and the square kilometer array, is designed to tease out that faint signal. When they succeed, they will create a three-dimensional map of neutral hydrogen across the first billion years, showing exactly where and when the fog lifted. A third, More direct method examines the chemical fossils of the first stars. Most of those ancient giants are long gone, but some of the stars they seeded are still shining today. These are the extremely metal-poor stars, born from gas that had been enriched by only one or a few supernovae. Their atmospheres preserve the chemical fingerprint of those early explosions. One famous example is a star catalogued as HE 1327-2326. It contains almost no iron, but it has an unusually high amount of carbon. That pattern matches the yields predicted from a pair-instability supernova of a very massive first star. Each such star is like a time capsule, telling us exactly which elements were forged and scattered in those first explosions. By studying a population of these pristine stars, astronomers can reconstruct the chemical evolution of the early universe, star by star. The most direct view of the cosmic dawn comes from the James Webb Space Telescope. Orbiting 1,000,000 miles from Earth, this observatory is designed to capture infrared light from the most distant galaxies. In its first few years of operation, Webb has already detected galaxies that existed less than 400 million years after the Big Bang. Some of them are surprisingly bright, suggesting they contain millions of stars already enriched with metals. This means the first stars must have formed even earlier, perhaps within 200 million years of the Big Bang. Webb is also seeing the ionized bubbles around those early galaxies, confirming that reionization was driven by starlight. The telescope can even measure the chemical composition of these galaxies, revealing the metals produced by the first stellar generations. Beyond galaxies, astronomers hope to catch the supernova explosions themselves. The first stars were so massive that their deaths produced incredibly bright explosions visible across the universe. A single pair instability supernova at a redshift of 10 or higher could be detected by future surveys. Gamma ray bursts, the intense flashes produced by collapsing massive stars, might also provide a beacon from the earliest eras. Detecting one of these events would allow astronomers to study the environment around the burst, including the chemical makeup of the gas, directly linking it to a population 3 progenitor. Each of these methods has its own strengths and limitations. The cosmic microwave background gives a global timeline. The 21-centimeter signal provides spatial detail. Metal-poor stars offer chemical insight. Webb gives direct images of galaxies. And supernova or gamma-ray burst detections offer time-resolved snapshots of individual events. Together they form a web of evidence, cross-checking one another, gradually filling in the blanks of a story that began almost 14 billion years ago. The excitement in this field is palpable. Every new observation, every deeper survey, brings us closer to the moment when we can say with confidence, we have seen the light of the very first stars. And maybe, someday soon, we will hear their echoes in the radio static, read their chemical signatures in the oldest stars, and witness their explosions from across the cosmos. The gas between galaxies never returned to its original state. Once the first stars ignited and exploded, they permanently transformed the medium that filled the void between them, what astronomers call the Intergalactic Medium, or IGM. Before those stars, the IGM was a uniform, cold, neutral fog of hydrogen and helium, with no variations in temperature or density across vast expanses. But the ultraviolet light from the first stars carved out ionized bubbles, and the supernovae injected heavy elements, shattering that uniformity forever. The IGM became a patchwork of hot ionized plasma, with pockets of cooler neutral gas persisting only in the densest regions, like inside dark matter halos where gravity shielded them from the harshest radiation. This new complexity meant that the IGM was no longer a quiet backdrop. It became an active participant in cosmic evolution. Temperature and density variations across the medium influenced how gas could cool and collapse into future galaxies. A region that had been heated by a nearby supernova might remain too hot to form stars for millions of years, while a cooler pocket elsewhere would see rapid collapse. The chemical enrichment was equally uneven. Some areas received a heavy dose of carbon and oxygen from a pair instability supernova, while others remained nearly pristine, still holding on to the original hydrogen and helium. This patchy distribution of metals meant that the next generation of stars formed in a chemically diverse environment, leading to a wider range of stellar masses and lifetimes. The transformation was irreversible. The universe could never go back to that simple state. Every future galaxy, every planet, every living thing would inherit the signature of that first transformation. The IGM became a dynamic, structured web with filaments of hot gas connecting the growing galaxies and voids of empty space in between. That cosmic web, shaped by the first stars, would guide the assembly of all later structure. The stage was set for the emergence of the large-scale structure we see today: clusters, superclusters, and the vast, empty spaces that separate them. And the engine driving it all was the light and fury of those ancient, long-gone giants. Those ancient giants were the first sparks that lit an enduring fire. Before they appeared, the universe was a cold, uniform fog of hydrogen and helium stretched evenly across space. There were no galaxies, no clusters, no heavy elements, no seeds of complexity. It was a blank canvas, empty of all structure. The first stars changed that forever by flooding the cosmos with ultraviolet light, by heating vast regions of gas, by scattering newly forged metals in every direction, and by blowing shock waves that compressed and sculpted the surrounding matter. Each of these effects worked together like a symphony of transformation. The ionization carved out bubbles of transparency, allowing light to travel freely and linking distant regions. The heating raised the temperature of the intergalactic medium, preventing gas from collapsing too quickly and regulating the pace of star formation. The chemical enrichment gave future generations of stars the ingredients to form planets and eventually life. And the feedback from supernovae and radiation pushed gas around, creating dense clumps where new stars could ignite and clearing away material that might have stifled further growth. Without any one of these forces, the universe might have remained a simple, static place. But together, they turned a blank slate into a rich, dynamic structure. You can think of the first stars as the first sparks that fell onto a dry kindling. At first, only a few tiny flames flickered in isolated patches. But those flames spread, catching nearby tinder, growing into a fire that eventually consumed the whole forest. The fire here is the process of structure formation itself. Each spark ignited a new pocket of complexity, and each new generation of stars added more fuel, more variety, more intricacy. Over hundreds of millions of years, those scattered sparks merged into a single, blazing network of galaxies and clusters that we see today. The first stars were the seeds from which all later cosmic structure grew. They were the original source of order in a chaotic, uniform void. How do we know this story is true? We cannot go back in time to watch it happen. But scientists have built powerful computer simulations that recreate the early universe, starting from the conditions just after the Big Bang and tracking every particle of dark matter and gas as they evolve under gravity, radiation, and chemistry. These simulations show exactly how the first stars formed inside dark matter halos, how they ionized their surroundings, how they exploded, and how their metals spread. They predict the sizes and shapes of the first galaxies, the timeline of reionization, and the chemical signatures we should see in ancient stars. And when astronomers compare those predictions to real observations from telescopes like the James Webb Space Telescope, they match remarkably well. The simulations are like a time machine, letting us glimpse the moments before any light existed and then watching the first sparks catch fire. They confirm that without the first stars, the universe would still be dark and featureless, a silent ocean of gas waiting for a spark that never came. but the spark did come. And that spark transformed everything. Computer simulations are the only way to witness those ancient flames directly. Even the most powerful telescopes cannot see the very first stars as individual points of light. They are simply too far away, too faint, and too brief. By the time their light reaches us, it has been stretched and diluted across billions of light years. So astronomers build virtual universes inside supercomputers, recreating the conditions of the early cosmos and then watching how they evolve over millions of simulated years. These cosmological simulations treat gravity, hydrodynamics, and chemistry all at once. They track every parcel of gas and dark matter, allowing scientists to push play on the cosmic clock and see structures form from scratch. Within these digital worlds, the first stars ignite under the same physical laws they followed in reality. The simulations reveal that these stars were not a single type, but a range, with masses between a few tens and several hundred times the mass of our Sun. The exact mass depended on how efficiently the primordial gas could cool through molecular hydrogen. That cooling, as we saw earlier, was slow and weak, which prevented the cloud from fragmenting into many small pieces. So the simulations consistently produce a population of massive stars, confirming that the first generation was dominated by giants. The simulations also capture the dramatic feedback from these stars. As the stars begin to shine, their intense ultraviolet radiation heats the surrounding gas and drives it outward. That feedback can shut off further star formation in the same halo for millions of years. When the stars explode as supernovae, the simulations show how the blast waves sweep up material and scatter heavy elements into the intergalactic medium, enriching vast volumes of space. All of this happens in the simulation, step by step, in a way that telescopes cannot directly observe. But simulations have their own limits. They can only resolve structures down to a certain scale. If the simulation grid is too coarse, it might miss the small clumps that could form lower mass stars. And many of the physical processes, such as how gas condenses into a protostar, rely on subgrid models that approximate what happens below the resolution limit. The chemistry of molecular hydrogen formation is also simplified in some simulations. These uncertainties mean that no single simulation gives a definitive answer. But by running many simulations with different assumptions and comparing them to the small handful of observations we have, astronomers can narrow down the possibilities. For the James Webb Space Telescope, simulations are an indispensable guide. They tell Webb where to look, at what wavelengths, and for how long. They predict the spectral signatures of the earliest galaxies, which Webb then tries to match. When Webb detects a galaxy from just 300 million years after the Big Bang, simulations help interpret that light, determining whether it comes from a population of massive stars or from a more extended burst of lower mass stars. The simulations have already predicted that the first galaxy should be surprisingly bright, a prediction Webb has confirmed. As Webb continues to push deeper, simulations will be refined and our picture of the first stars will become sharper. The virtual universes we build today are the scaffolding on which tomorrow's discoveries will rest. They are not just a tool for understanding the past. They are a bridge between what we can observe and what we can only imagine. Yet despite all we have learned, the first stars remain wrapped in some of the deepest mysteries in modern astronomy. We know they existed, we know they transformed the universe, but the details of their lives are still frustratingly blurry. One of the biggest open questions is their exact mass range. Simulations suggest they were massive, but how massive? Were most of them 50 times the mass of our Sun? Or did some reach 1,000 solar masses? Did they form mostly alone, as isolated giants? Or did they gather in small clusters, like a handful of campfires in a vast forest? These questions matter because the mass of a star determines everything: how long it lives, what elements it produces, and whether it dies in a supernova or collapses directly into a black hole. Without a firm answer, our models of early chemical enrichment and galaxy formation remain uncertain. Another mystery involves their social lives. Did the first stars form in binary systems, orbiting one another, or did they appear as solitary beacons? In the modern universe, most stars are born in pairs or groups, but the unique cooling conditions of primordial gas might have favored single, isolated stars. The number of binaries affects how many supernovae occur, how many black holes merge, and even the rate of gravitational wave events we detect today. The efficiency of reionization is another puzzle. We know the first stars ionized the intergalactic medium, but how efficiently did they do it? Did each star clear a large bubble, or was the process slow and patchy? The answer depends on how many ionizing photons escaped the dense gas around each star, and that escape fraction is hard to measure. Some models say it was high, others low, and the difference changes the timeline of the cosmic dawn. There is even a more exotic possibility: dark matter annihilation. Some theories suggest that dark matter particles, when they collide, can annihilate and release energy. If this happened in the dense cores of early protogalaxies, it could have heated the gas and altered star formation. Could dark matter have helped or hindered the birth of the first stars? We do not know, and the answer could reshape our understanding of dark matter itself. And finally, the most glaring mystery: why do we see so few direct signatures? Despite decades of searching, we have not yet detected a single individual. Population 3 star. They are too far away, too faint, and too short-lived. Their light is stretched into the infrared and buried under the glow of later galaxies. Even the James Webb Space Telescope, for all its power, has not yet caught a lone first star in action. The evidence we have is indirect: the chemical fingerprints in ancient stars, the polarization of the cosmic microwave background, the light from early galaxies. These clues are compelling, but they are not a direct photograph. The persistence of these mysteries is not a failure of science. It is a reminder of the challenge. Observing the first stars means looking back more than 13 billion years to a time when the universe was less than 1% of its current age. Their light has been traveling for almost the entire history of the cosmos. It has been stretched, scattered, and diluted by expansion. Any signal we hope to catch is vanishingly faint, like trying to hear a single whisper in a hurricane. But the chase is what drives the field forward. Each new telescope, each new survey, brings us a step closer to lifting the veil. The square-kilometer array promises to map the neutral hydrogen of the cosmic dawn in radio waves, showing us the structure of reionization in 3 dimensions. The Nancy Grace Roman Space Telescope will survey vast areas of sky, catching the light of early galaxies that Webb can then study in detail. And future observatories, like the proposed Origins Space Telescope or the Advanced Telescope for High-Energy Astrophysics, may one day capture the afterglow of a pair instability supernova from the first stars. We are on a cusp of answers that have eluded us for decades. Each unresolved mystery is a door waiting to be opened, and the keys are being forged right now in laboratories and control rooms around the world. The first stars may be hidden, but they are not silent. And we are learning to listen more carefully every day. Telescopes are finally catching those faint whispers. The James Webb Space Telescope, positioned 1 million miles from Earth, has already detected galaxies from less than 400 million years after the Big Bang. Those distant smudges of infrared light contain millions of stars each, and their spectra reveal chemical fingerprints that hint at enrichment from the very first supernovae. Astronomers comb through Webb's data, searching for the telltale signature of pure hydrogen and helium gas uncontaminated by metals. A galaxy with almost no metals would be a direct signpost pointing to the remnants of population-free stars still burning inside it. So far, the hunt has not returned a smoking gun, but the data keep pouring in. Every new image, every new spectrum brings the possibility closer. Beyond Webb, the Nancy Grace Roman Space Telescope is preparing to launch in the late 2020s. Roman will survey huge swaths of sky at infrared wavelengths, capturing thousands of the earliest galaxies in a single sweep. Where Webb peers deeply into tiny patches, Roman will map the landscape broadly, providing the census that tells us how many galaxies existed at each stage of the cosmic dawn. Meanwhile, the Square Kilometre Array, a network of radio dishes spread across Australia and South Africa, is being built to detect the faint radio whisper of neutral hydrogen from the epoch of reionization. Astronomers call this the 21-centimeter signal. By mapping how that signal fades and shifts across the sky, the Square Kilometre Array will create a three-dimensional movie of how the first stars carved holes in the neutral fog. It will show us not just when reionization happened, but where it started and how it spread. Behind the scenes, computer simulations are growing more powerful and more realistic. Earlier models treated stars as simple points of light, but modern simulations include radiation hydrodynamics, tracking how ultraviolet photons move through gas, heating it, ionizing it, and pushing it around. These simulations also model the feedback from supernovae in exquisite detail, following the shockwaves as they enrich the surrounding medium with heavy elements. They can now resolve the formation of individual protostars inside collapsing clouds, capturing the moment when a clump of gas becomes hot enough to ignite fusion. This level of detail helps astronomers predict what Webb and the Square Kilometre Array should see. It creates a tight feedback loop between theory and observation. The simulation suggests where to aim the telescopes and for how long. The observations then test those predictions, forcing the models to improve. Each cycle sharpens our understanding. The next decade will likely revolutionize what we know about the first stars. Webb has only just begun its mission. The Square Kilometre Array is still under construction. Roman has not yet launched. And new theoretical breakthroughs are emerging all the time, from the role of magnetic fields in primordial gas to the possibility of dark matter annihilation influencing star formation. The questions that remain unanswered today are precisely the ones that drive this field forward. Every unresolved mystery is a door waiting to be opened, and the keys to those doors are being forged in observatories and supercomputers around the world right now. The first stars may be hidden, but they are not silent, and we are finally learning to hear them. The story of the first stars is also the story of our own origins. Every atom of oxygen in your lungs, every carbon atom in your cells, every calcium atom in your bones was forged inside a star that lived and died billions of years before our sun was even a dream. Those first ancient giants were the original element factories. When they exploded as supernovae, they scattered the building blocks of planets and life across the cosmos. The iron in your blood, the nitrogen in your DNA, the silicon in the ground beneath your feet, all of it came from those long-gone furnaces. Without the first stars, the universe would have remained a simple place, filled only with hydrogen and helium, incapable of forming anything more complex than a cloud of gas. There would be no rocky worlds, no oceans, no atmosphere, no life. The transformation they set in motion was not just a cosmic event. It was the necessary precursor to everything we cherish about existence. The first stars turned a blank, sterile void into a fertile garden. They created the conditions for complexity to emerge, for galaxies to assemble, for planets to form, and for consciousness to one day look back and wonder at its own origins. You and I are not just observers of this story. We are its direct descendants. The atoms that make up our bodies traveled across space and time, carried by the shock waves of ancient explosions before finally gathering together on this small world. To understand the first stars is to understand where we come from. They were the architects of structure, the original source of order in a universe that began as nothing but chaos. And the next time you look up at a clear night sky, remember that the light you see has traveled a long road. But the deepest light of all, the one that made all other light possible, comes from stars that have long since faded into memory. Their legacy is written in every breath you take. That transformation from darkness to light is the most profound shift the universe has ever known. In the beginning, there was only a cold, uniform fog of hydrogen and helium stretching across an endless void without a single point of light. Then, inside the gravitational wells carved by dark matter, the first stars ignited. They burned furiously, lived briefly, and died in spectacular explosions that scattered the seeds of complexity across the cosmos. Those ancient giants ended the cosmic dark ages, punching holes in the neutral fog and flooding the universe with ultraviolet radiation. They drove reionization, turning an opaque haze into a transparent medium where light could travel freely. And in their deaths, they forged the heavy elements carbon, oxygen, iron that would later assemble into planets, oceans, and life itself. Every star that shines today, every galaxy that swirls through space, owes its existence to those first sparks. The universe went from a blank canvas to a masterpiece of structure, all because a few massive stars dared to burn. Before you go, take a moment to reflect on that connection. The atoms in your body were once part of those ancient explosions. You are not separate from this story. You are its continuation. If this journey through the cosmic dawn sparked your curiosity, hit the like button, subscribe to the channel, and leave a comment telling us what part of the early universe fascinates you most. The first stars may have faded from sight, but their light still echoes across billions of years, and we are still learning to listen. In the end, we are all stardust that learned to wonder about where it came from